Hello, my name's Gerald Vincent, and I'm going to be talking a little bit about the project I did for my PGM class. And I kind of calling it Vocalizing Actions using PGMs to turn voice commands into actions. All right. So the idea behind this project was to take voice commands from a user and basically translate those into a set of actions that a given agent, represented by A here, could take in a given kind of grid game like this, with the object of a user using voice commands to take agent A through this sort of maze all the way to their goal. Um, Now, obviously, this is a fairly simple thing to do using traditional programming, but I wanted to be able to use the voice commands and really with using PGMs, train probabilistic graphical models to learn the right actions given a lot of information that's available in the voice command without having any prior knowledge of how this game is played. So basically, somebody would open up the game, it would go like this, and they might say simple voice commands such as like move right. And of course, the intended action would be to move this agent right. Then they might say something like move down 2 steps, move right 1, move down 1, move right 1. And this set of this big PGM and some of the techniques need to be able to translate those voice commands into those desired actions. Now, kind of a high-level overview of the model that I built was it combines not just the voice commands, but a lot of available info that we have about the game state as well. I'll start with the voice commands. So basically, the process is to take raw voice audio, use the CMU Sphinx, I think Pocket Sphinx version, to translate that using their pre-trained models into a set of likely phrases. I pick like the top 5 phrases. Then I actually translate those into character forograms for a variety of reasons, such that the individual phrases themselves aren't quite so sensitive to minor changes. And also with character forograms, you get some idea of 2 words, kind of 2 n-gram words, because you can capture characters from both sides. That was actually a technique that I learned about in my information retrieval class. But then basically do a probabilistic model that says based on the probability of different forograms being said, what's the potential desired action. Another thing that was done was we take the local game state. So we take the terrain available to the north, south, east, and west of the agent and turn that into probable desired actions. And then there's a couple things about, especially with these actions that can take place over 2 steps, such as, move the agent down 2 steps. You need some information from previous iterations. So one thing is to just use the character forograms at T1 along with the previous action at T1 and turn that into a probability distribution, and then also do a hidden Markov model on the previous actions in that game all the way up to that state. And basically what you do is you have these, each one of these branches are treated as independent. You calculate all 4 of these different probabilities and then blend them together. All right. Okay, so go ahead and gonna review the code for this. I decided to write this code in Python because it's a language I've become pretty familiar with in my time at Johns Hopkins. So just a couple things to note. It does require Pocket Sphinx, a couple other libraries for it to work. If you are trying to get this running, it should be listed on the GitHub requirements as well. There's a couple of key classes. So one of the first classes is the random game state. This is a class that basically tracks that 2-dimensional array of what the game state terrain is, randomly initializes it, keeps different actions, as well as has the ability to update the game state, agent location, goal location, etc., given somebody's actions. So those actual actions that are given. Also has the ability to produce a local state representation, this terrain immediately around the agent for use in some of the models. And then there's a couple other helpful functions. This is where the game state gets rendered to the console, and also a check for whether the game is over, aka if the agent is on the goal. To have another model, another class called the voice model. I'll start off with the. Sorry about that. I'll start off with the second function here, our second method in voice model, which is the process voice. So this is what actually turns the detects the voice via an audio and turns that into like this decoder object. And then it calls another function within this class called phrase probabilities. And what phrase probabilities does is basically takes that decoder object, gets the top, say, I found that it worked pretty well with 5 results. So these are going to be the 5 likely phrases. And then it's going to basically, using kind of like a linear interpolation, it's going to turn those into different probabilities of each phrase being said. I couldn't use the raw probabilities, hence the heuristic coming out of the CMU Sphinx, because of the way they were using that model. The difference in probabilities between the top result and the next couple results were sometimes many orders of magnitude, and those just didn't really add a lot of value. And what I was seeing was that the actual phrase that was said oftentimes was in those lower probability phrases. So I decided to use this approach, really to just get it to work. There's a couple other functions that'll be used later, such as wait for override, log data, parse log data. These are just different helper functions for actually running the game and then logging results. And here there is a helper function for translating those likely phrases that get pulled out into character forograms, and basically putting in the probability that any of those forograms was actually part of a phrase that was said. So part of the reason, like I said, using forograms, there's a nice little paper here. It's basically a nice way to not have to deal with word stemming and other things, but still kind of capture the most of the essence, or average essence of a given phrase. Worth doing some research if you're interested in that sort of thing. I do have a kind of a general class that I hand wrote just for the way I was doing this, with some of the confidence in different variables. It was easier to do this with the joint probability distribution. Basically, there's like a left-hand side, which is some set of observed values and some set of confidence in those, that evidence, and then the right-hand side, which in this case is always the possible actions. So I was able to use that construct to kind of simplify things. Basically, we have that. There's a way to add data to there. So given some set of possible values that we're seeing and the confidence that those values were seen, you can build joint probability distribution to see those and the observations. One thing that's interesting is, because these are like forograms in a phase, is that each row is not necessarily mutually exclusive. So you can have multiple rows be active in that probability table. And then once again, there's a method for kind of putting in a new phrase and then evidencing that into the probability distribution and getting the probabilities out, normalized probabilities out. I won't go into details there, but it does work. Finally, as far as classes go, there is the desired action model. This is basically the probabilistic model that predicts your actions. It's not too complicated, actually. It looks a little bit more complicated than it really is. There's voice to action model, terrain to the up, left, right, and down models. There's the previous voice action model, so the previously likely phrases from the previous iteration, and then the hidden Markov model, predicting a sequence of potential actions. The code here really just parses that data from the log file of previous trained iterations and builds or initializes these models correctly. And then the predict function takes a set of likely phrases, the current game state, and then the likely phrases from the previous iteration, and evidences that all into the graphical model and returns a set of probabilities, whether you want to go left, right, up, or down. Another couple helper functions, combining and normalizing, also a nice fancy print function. And we're to the main loop. Main loop is pretty easy. Games, you initialize a game state, initialize a voice model and initialize the desired action model, initialize previous likely phrases to none, and then render the game state, process the voice, predict the likely outcomes, get the most likely outcome, and let the user know that's the action that's going to be taken. If they're in an override situation, allow them to override those commands if you're trying to train the model instead of just using the model. And once you get the actual action, you update the game state and record the previous likely phrases. Once the game is done, you log the data, allow the user to either quit or run another game, and that's that. That's all the code. Okay, so really quickly, I'm going to show kind of how I trained these models. Basically, I trained the models by really just running through them and then providing user overrides. Looks like the agent started out right on the goal that time. All right, so move down one space. As you can see, it has no idea what I'm talking about, so it's going to guess that I want to go left. Here I'm going to say, I actually want to go down, which is S and WASD keyboard. I'm going to press S and press Enter. And yay, I found the goal. And basically I'm going to run through this a bunch of different times. Now I've already done this, and I actually ran through this model 77 times, or through 77 different games. I'll be showing you that in a second, but I'll run through one more example so you get a better idea. Move up one space. Move left 3 spaces. Move left 1 space. As you can see, it's still very dumb. I started seeing some decent results around about 20 games played, and then right around 50 to 75 games played. That's what you'll see next, but actually get really good results. Ability to play without any overrides, actually. So we'll see that next. Okay, so next we're going to go ahead and see what this looks like when you use it with the trained model. So I'm going to call the main, and I'm going to say override is false. So that means that we'll be using only the voice to action model and no override. So go ahead and start that. It's going to ask me to say voice command. Go down once. Go down twice. All right, as you can see, I was able to interpret the first command, even a command that really was 2 separate iterations. So I'll go ahead and run one more game just to kind of give you an example. Go up twice. See, that was another simple example, so hopefully we get a better one this time. Go right twice. Go down once. There we go. One more time. Go up once. Go up 3 times. Go left once. See, so as you can see, it's not the most amazing thing, but It does actually, between using the different models, the different information available, as well as training on about good number of examples, it actually works pretty well. So that's it for my presentation. Just wanted to say that I really enjoyed this class. I learned a lot from this class, and as you can see, hopefully able to apply some of the context or some of the contents of the class in a real-world example. Um, so this is my last semester at Johns Hopkins. It's been a really great experience, and I appreciate really everything about it. So thank you. I hope you enjoyed my project.